Hello everyone, so welcome to lecture number 12. So we have been seeing so the idea of what is called driving force, and we said we just looked at the change in G as a function of pressure, and then we said there are two phases that will compete. So which phase wins and at what pressures, right? So that's the question that we were asking, right? So we just asked the question to start with in the last class, which phase wins at what pressure, right? And the only variable that we were changing is pressure, is the only external variable that we are changing. And as a result, so we came up with these sort of, so and then we said dg, the is equal to dp, but that depends on v, right? And v alpha, if I am talking about alpha phase, so that becomes dg alpha, and if I am talking about beta phase, that becomes v beta dp, right? And we said, what did we say exactly about alpha and beta? If I go back, I am going to say that beta is the low volume phase, or it is the more rarer phase. Beta is the less dense or more volume phase. By volume I mean specific volume, and specific volume V equal to capital V by capital N. N is the number of moles. This is specific volume, and specific volume of beta phase is larger, which means you can assume that beta is like a gas phase, like example, and alpha is like a solid phase or a liquid phase, right? So, I mean the exact phase definitions can change. Beta in general has a larger volume than alpha. So in general beta can be an amorphous phase and alpha or glassy phases. Alpha can be a crystalline phase. Okay. So, alpha is typically a low volume phase and beta is a high volume phase, right. Okay. So, with that then we said, if I just let me just go back here and plot finish this plot. So, so beta wins at low pressures, right. So, this is as a function of pressure, and beta has a larger volume. So, this is going to go like this. This is G beta. G alpha is going to be like this because alpha has a low volume. The slope of this should give the volume of that phase, right. So, let me make it a bit more convenient that we are changing, and here let me write dg alpha equal to v alpha dp, dg beta equal to v beta dp, and so so I am going to draw g beta with a higher slope, right. Let me change the color otherwise. So, let me use this color. G beta comes up with a higher slope and G alpha comes up with a lower slope because it is a low volume phase, and you can see that at low pressures, this is my equilibrium pressure, right. At P less than P equilibrium, so G alpha is less than G beta, so alpha wins, okay. And then we said that delta G, which is equal to G alpha minus G beta, right, that gives me, that is this value, right. So, at this pressure, let us say at pressure P1, G alpha minus G beta, but I define which is negative, which means if I have beta at pressure P1, at time t equal to 0, which means so at time t equal to 0, if I have a beta phase, right, at pressure P equal to P1, then it is just a matter of time before which it converts to alpha. Then it is just a matter of time before which it converts to alpha, right. So, sorry, maybe the other way around. Sorry, beta is less, right. So, if I have I am sorry, I wrote this wrong. Beta wins, beta is the low volume phase, beta wins. So, G beta is less than G alpha, G beta minus G alpha is less than 0, which means if I have an alpha phase, right. So, if I have a solid phase at 0 pressure, eventually, so it is just a matter of time that it degasses and becomes a beta phase, before which it converts to beta, right. So, for the alpha to beta phase transition, delta G is negative, right, and this is important. Then I have defined capital delta, this G as minus delta, this G, right. This is my thermodynamic delta G, and this I call it to be the driving force, right. If the driving force is positive, then my reaction is spontaneous, or in this case the phase transition. Then if driving force delta G equal to 0, right, then both are then that is called the equilibrium, that is so alpha and beta are at equilibrium, right. So, I mean again going back to this curve, right. So, this is G beta, this is G alpha at P1, right. So, at P equal to P1, beta is stable, okay. So, again just to repeat, at time t equal to 0, if I have an alpha phase or a solid phase, thermodynamics is going to say that solid should eventually degas, solid should eventually degas into beta phase, okay. And as a result, I am going to construct what is called my first phase diagram, right. And this phase diagram is just so the only variable I am changing is pressure, the only measurable variable I am changing is pressure. Below P equal to P equilibrium, I have the beta phase. So, here this is the beta phase and this is the alpha phase, that is it, right. So, this is my first phase diagram. The only change, the only variable that I can change is pressure. This is all at a constant temperature, right. At this pressure below P equilibrium, I have beta phase, and above P equilibrium, I have alpha phase, right. Alpha phase is the low volume phase, beta phase is the high volume phase. This is like solid, this is like gas, right. We gave another example is coal converting to diamond, right. Coal is the low volume phase, diamond is the high volume phase. And here if I write delta capital G, delta script G is V of coal minus V of diamond, and that is a positive quantity, right, times P minus P equilibrium, right. And this P should be larger than P equilibrium for delta G is positive only if P is larger than P equilibrium, which means diamond turns out to be a high pressure phase. Okay. So, let us say some 20 GPa or something is, or I do not really remember, but let us say some P equal to 200 GPa is a pressure that I should apply to form diamond, right. So, I take coal right, and then because of some volcanic processes that happened some 10,000 years ago, this coal has gone down and there is some pressure that is being applied on this coal, right. And if that pressure is something greater than, I am saying 200 gigapascals, I do not know what these geological pressures really are, but it is large pressure, that much I know, right. So, maybe it is one order of magnitude less, I do not know what this number is. Okay. So, let us just call it P2, right. If the pressure is greater than P2, P is greater than P2, then the pressure applied by all these volcanic processes, all the earth's crust etc. on the this coal, then beyond a certain time, say 3000 years or 4000 years, I am getting diamond, right. So, just because of phase diagram, right, I have the sufficient overpressure. And by overpressure in this I mean the driving force, right. So, overpressure, driving force, all these means the same, right, to create diamond from coal. So, it is just a matter of time. Before which this happens. Okay. So, this is what we said in the last class, right. Okay. So, okay. So, that is with respect to pressure. Now, let us do another case study, case 2. Now, the only variable, so I have alpha and beta phases now, right. Again, alpha is like a solid phase, beta is like a gas phase, let us say, or alpha is solid, beta is liquid, something like that, right. So, or in other words, alpha has lower entropy, right, solids have lower entropy than gases, right, and beta has a higher entropy. Okay. Typically, lower entropy corresponds to higher volume, lower volume, and lower higher entropy corresponds to higher volume, but it is not always the case. In case of water, this is not valid. Okay. So, we will look at that phase diagram later. Okay. So, now the only variable I am changing, only variable is temperature. Okay. So, then we can exactly write the same thing, dg alpha equal to minus S alpha now times dt, and dg beta equal to minus S beta times dt, right. Now, I sort of if I am plotting g as a function of t, I sort of know that at lower temperatures the phase that wins, or the phase that has a lower g, is the it is like ice, right, it is the solid phase. So, the phase that has lower entropy wins at lower temperatures, the phase that has higher entropy wins at higher temperatures, right. So, that is essentially. So, so I have g beta, if I am just drawing g beta as a function of temperature, g beta is going to decrease, it has a larger entropy, right. And then if I am going to draw g alpha as a function of temperature, g alpha is going to also decrease, but with a lower entropy. Sorry, this is g alpha and this is g beta. Okay. Just based on the slopes, this is g beta. Just based on the slopes, you can say that this is the equilibrium point, T equilibrium, right. Below T equilibrium, the alpha phase is stable, T less than T equilibrium, alpha is stable, T greater than T equilibrium, beta is stable, or beta is the equilibrium phase, right, and beta is the high volume phase or high entropy phase like a gas, and alpha is a low entropy phase. Okay. So, then we can of course, do whatever we did earlier, and that is find the driving force or the so what is the delta G, right. So, let us say I am at this temperature, and to start with I am in a beta phase, right. So, what is the delta G for or the driving force for me to form the alpha phase, that is what I am going to write. Okay. So, delta G for alpha to beta phase beta to alpha phase transition, right, that is equal to I mean we can also beta to alpha, that is equal to G alpha minus G beta, right, and G alpha minus G beta is delta G at T equal to T equilibrium, that is equal to 0, plus d delta G. Now, delta G is always going from beta to alpha by dt delta T. This is the same Taylor expansion that we did earlier. Okay. Now, that is equal to 0 plus, because at equilibrium G of alpha equal to G of beta. So, at this point this is 0, d delta G by dt, right. So, that is d G alpha by dt minus d G beta by dt. So, that is equal to minus S alpha minus S beta, right, minus of S alpha S beta times delta T. Now, what is delta T? Delta T is T minus T equilibrium, right. So, that is the delta G for beta to alpha. For conversion of beta phase into alpha phase. Okay. So, it is minus S of alpha minus S of beta, right. Now, that is a negative number, because S of alpha is less than S of beta, right. So, minus of that is a positive number times T minus T equilibrium, right. So, this entire thing, or I am going to write it as S beta minus S alpha times T minus T equilibrium. Okay. And S beta minus S alpha should be evaluated at T equilibrium, right. So, that is what Taylor expansion means. This is to be evaluated at T equilibrium. When I move slightly away from equilibrium, what is the delta G? That is what I am looking at. Okay. Okay. So, if T is less than T equilibrium, beta phase forms, right. Even if I beta to alpha, right. I am sorry. So, this is going from this is beta to alpha, right. So, alpha phase forms, alpha is like my solid phase. So, this is not beta phase, right. So, if this is like saying if temperature is less than 0 degree Celsius in case of water, right. So, temperature less than 0 degree Celsius, ice is the stable phase, right, and ice has lower entropy than this is a lower entropy phase than water. T greater than 0 degree Celsius, then I have liquid phase, or water is the stable phase. Water is like my beta phase, right. This is a higher entropy phase. Okay. So, then what is the driving force, right. So, okay. So, let us go back to delta G equal to S beta minus S alpha times T minus T equilibrium. Now, this is a negative quantity if T is less than T equilibrium. Okay. So, I can as well then define a delta script G, this is my driving force, equal to minus delta G, and that is equal to S beta minus S alpha times T equilibrium minus T, right. Now, this delta G is positive if T is less than T equilibrium. So, alpha phase forms spontaneously, right. So, thermodynamics says alpha phase should form. Okay. And how much T, the temperature at which I am operating, is less than T equilibrium tells me how fast does a beta phase convert to alpha phase. And now it is easy to give you an example. I have water, right, in a container. This water is to start with, it's at some temperature greater than so this is a temperature equal to 5 degrees Celsius, right. Now at T is the time equal to 0, temperature is said to be minus 5 degrees Celsius. Okay. Now if it is said to be minus 5 degrees Celsius, it should eventually, right. So if I am following some kind of what is called an order parameter, or how much volume of ice that is formed, if I am divided by total volume, right. So initially there is no ice, and but at some point there will be ice that is formed, right. So it is going to form, we'll look at these, right. So this is we'll look at these sort of diagrams again, but initially ice is not formed. Initially there is some ice that is being formed, there is some more ice that is being formed, and eventually the ice sort of succumbs, right. So the volume of ice by total volume becomes 1, right. It starts with a 0 and it becomes 1. This is at 5 degrees Celsius, minus 5 degrees Celsius. But if I change the temperature now, if I change it to some minus 20 degrees Celsius, if at T equal to 0, the temperature is then set to, this is another case where at T equal to 0, the temperature is suddenly cooled down to minus 25 degrees Celsius. What would you expect? Ice is formed more faster, right. So ice is formed even more faster than ice was formed before. So so I can plot that, and I can say that, look, the ice actually forms much faster, right. So this is at minus 25 degrees Celsius, right. So the higher I go, the lower the temperature is, right. So or T equilibrium minus T, that value, right. So the higher this value is, the faster is ice formed. Formed meaning, so there is some kinetics happening here, nucleation and growth. We will look at it later on, but just to give you an idea, this person here, T equilibrium minus T, right, that determines how fast, or that determines my driving force, delta G, delta script G, for the ice to form, right. The higher it is, the higher is the driving force, and so faster is the ice, right. So that is how it works, and this quantity then is called undercooling, right. Now when I say I need some undercooling, I actually mean that I need some delta G, driving force, right. So I have to form the low temperature phase and to form, or the low entropy phase, and the low entropy phase turns out to be stable at lower temperature. So compared to the equilibrium temperature, how much is my undercooling, so that I am forming this phase, and how fast am I forming it, right. So this is what all these things mean. Undercooling essentially is used in context of forming a low temperature phase, right. So and how much undercooling I need from the equilibrium temperature. At equilibrium temperature, it takes infinite time for me to form this undercooled phase, but at finite temperature it takes me finite time. And what is that time? That time is determined by this delta G, which is the driving force, and undercooling is a proxy here, because temperature is is the variable that is changing. So undercooling is a proxy for my driving force, right. So in this case, undercooling is a proxy for my driving force. Okay. Similarly, if I want to form a high entropy phase, I have to go so then the delta G will be for beta to alpha. So then I need overheating, not undercooling. Okay. So that is if I want to form a high temperature phase. All right. So then here is my second phase diagram, which I am just drawing as a function of temperature, right. Less than T equilibrium, I have the alpha phase. Greater than the T equilibrium, I have the beta phase. So I am just looking at which phase is stable at what temperatures. That is the phase diagram, right. So and the control variable here is temperature, right. So with respect to temperature, which phase is stable at what temperature, right. So this is a one dimensional phase diagram. The only variable that is changing is temperature. Okay. So with temperature below T equilibrium, which is like 0 degrees Celsius, I have ice, above 0 degrees Celsius I have water. Okay. Now let us go back to this delta G equal to S beta minus S alpha, this is for beta to alpha, dy times T equilibrium minus T, right. So, this is the driving force equation for beta to alpha. Now, S beta minus S alpha, this is taken at T equilibrium. What is this number? Right. So, this is delta S between the beta phase and the alpha phase, right. So, what is the difference in entropy between the beta phase and the alpha phase, right. If we go back to the definition of S, S is nothing but this is how much beta phase has more entropy than the alpha phase. Why does beta phase have more entropy? Because beta phase has more latent heat, right. So, at the phase transition there is more latent heat in the beta phase. We have actually plotted delta H or H as a function of temperature, right. So, this is the alpha phase, and when there is an alpha to beta phase transition there is going to be a delta H, which is the latent heat. I am going to call it as L. Okay. So, this latent heat because there is more heat in that, there is more entropy, and the way to get entropy from heat is just S beta minus S alpha equal to H beta minus H alpha divided by T melting point or T equilibrium, right. So, this is the equation that relates the latent heat with the change in entropy. These are one and the same. The entropy is changing means there is some latent heat, right. So, there is low entropy phase, high entropy phase, which means the high entropy phase has some more latent heat at the same temperature. Okay. So, instead of writing S beta minus S alpha, I can also write it as delta G equal to some latent heat term divided by T melting point or T equilibrium, right. So, in this case equilibrium I am looking at it as melting times T equilibrium minus T, right. Latent heat is a positive number, T equilibrium is a positive number. If this is a positive number, I have a finite driving force for the alpha phase to form. If this is a negative number, then I have a finite driving force for the beta phase to form, or alpha will not form. Okay. So, we will stop here this lecture, and then in the next class we are going to change both pressure and temperature, and then see construct now two dimensional phase diagrams. Now, I can change both pressure and temperature, and then see the phase stability, right. So, at what pressures and temperatures is my solid phase stable, at what temperatures and pressure is my liquid phase stable, and so on, right. So, we will continue a similar line of thought. Okay. So, now we will change both pressure and temperature. Earlier we were just changing one quantity, right. So, dG is changing by changing pressure, and we are looking at phase competition between the alpha phase and the beta phase. Okay. So, now we are going to change both pressure and temperature, and then look at the competition between the alpha phase and beta phase. Okay. All right. So, I will see you in the next class.